Come on, let us start our practice of numerical problems on transform. So the first problem is like this. The output power in a step-up transformer used in practice is the output power of a step-up transformer used in practice is dash. The first problem. So the four options are given here like this. Greater than input power. It is greater than input power. Second, it is less than input power. Third, it is equal to input power. And the last one is, it is equal to unity, equal to 1. What is the output power for step-up transformer used in practice? So dear students, remember this one, it is the answer that as efficiency is always less than 1. Efficiency is always less than 1. So, means less than unity. So in practice, the output power is less than the input power. The output power is less than the input power. So the option second is correct. This is the first question. Now, let us talk about the second one. A transformer is used to light 100-watt lamp. A transformer is used to light up a 100-watt oblique 100-volt lamp. A transformer is used to light up this particular thing. A transformer is used to light up a 100-watt 100-volt lamp from 220 volt mains. From 220 volt mains, means mains supply. If the main current is 0.5 ampere, if the main current is 0.1 ampere, the efficiency of the transformer is how much? Here is 0.5 ampere, comma, the efficiency of transformer is dash dash. The options are here 96%, B, it is 90%, C, it is 99%, and the last option is 95%. D is 95%. So dear students, to solve this particular problem, let us see here, the solution is like this. The output, the efficiency, the formula for the efficiency of a transformer is eta is equal to output power upon the input power. P output power, output power divided by P input, means input power, multiplied by 100. So this is the formula to calculate the efficiency. So 100 divided by 220 multiplied by 100, that is equal to 100 divided by 110 and that is nothing but 10 by 11 means 90%. That is equal to 10 by 11 means 90%. So see here, the option B is correct in this case. Now let us see the last problem of this particular topic, that is from transformer, is the third problem of the same case. A step down transformer has 50 turns on secondary. A step down transformer has 50 turns on secondary and 1000 turns on primary, has 60 turns on secondary and 1000 turns on primary. Yes. If a transformer is connected to 220 volt 1 ampere, if this transformer is connected to 220 volt and 1 ampere, hereby it is given as 50 turns. Make correction. Then AC source, then what is the output current of the transformer? Of the AC, then what is the output current of the transformer? This is the question. So see here, we have seen a formula, Ns upon Np is equal to Vs upon Vp. Solution to this problem is like this. Ns upon Np is equal to Vs upon Vp. Number of turns in the secondary are 50 divided by number of turns in the primary are 1000. Whereas the voltage in the secondary is to be calculated Vs, and this primary voltage is given as 220 volt. So Vs will be equal to, the 220 will be multiplied there and we will get 11 volts. And now this is not over. Again, what is the output current we have been asked? So Vs Is is equal to Vp Ip. Vs Is is equal to Vp Ip. So we are interested to find value of Is. So 11 into 1s is equal to 220 into 11 into Is is equal to 220 into the primary current is how much? 1. So in this way, Is will be equal to 220 divided by 11. So in this way, Is is equal to 11 to 22. So this is 20 ampere. So in this way, the current of 20 ampere we are getting as what is the output current in the transformer. So this is the output current in the transformer. It is 20 ampere. So this is about the practice on numerical problems based on need in the self-inductance and mutual inductance and transformer. So the rest part will be seen in the next, will be continued in the next video. Thank you very much. So dear students, today this is the third lecture in which I am going to continue or proceed the same chapter, that is electromagnetic induction, but the topic is now 16.5, that is coil rotating in uniform magnetic induction. So under this particular heading, we are going to see, we have to derive the expression. I mean, this one is also called as an AC generator. The same article can be asked as AC generator. So So let us suppose a rectangular coil PQ is placed in the uniform magnetic field of induction like this. Suppose this is uniform magnetic field of induction B, in which a coil PQ is placed. This is the axis of the coil. This is P and Q. Is nothing but a rectangular coil. So after time t second, the coil rotates in this particular magnetic field, and after some rotation, after a few seconds, it will come to this particular place. It is denoted by Q1, Q1. So it is revolving or rotating with the angular velocity omega. This is, and the angle made between them is theta. The angular velocity is omega. So now omega is equal to theta by t. So here omega is equal to theta by t. Therefore theta is equal to omega t. So at P1 Q1, the magnetic induction means composition will be B cos theta. The composition of magnetic induction at P1 Q1 will be B cos theta. So I am talking about this particular position. And now the flux produced will be given by the flux associated or produced is given by phi is equal to N A B cos theta, because the total number of turns are here. N A is the area of the coil, where B is the magnetic induction, and cosine of the angle theta between them. In this way, that is phi is equal to NAB. That can also be written as phi is equal to NAB cos. Instead of theta, we can write here omega t. So this is nothing but the flux produced due to the rotation of the coil. So again, this is called as equation 1. And now let us differentiate this equation. Differentiating this expression with respect to t, we get d phi by dt is equal to NAB is the constant. The derivative of cos theta is minus sine. Therefore, NAB into sine is become cos minus sine omega t into omega. So that can be written as d phi by dt. Omega is taken outside. NAB omega into minus. So minus sine is taken outside here. Sine omega t. So this is d phi by dt. Means differentiating that particular equation, we get like this. So this is equation number 2, suppose. Now let us go ahead to proceed. Omega is equal to 2 pi f. Putting in this equation, we will get. But omega is equal to 2 pi f. Putting this, in equation 2, we get d phi by dt is equal to minus NAB sine omega instead of omega we can write here 2 pi f into t. In this way, the equation for flux becomes like this. So in rotating coil, which produces an EMF, if the coil rotate, you might be knowing that the rotating coil produces an EMF, though we can write like this. E is equal to minus d phi by dt. Therefore, this E will be equal to minus d dt of phi. What is this? D phi by dt. Minus NAB sine 2 pi ft. So So that is written there, minus 2 pi f NAB sine omega t. That can be written like this, minus 2 pi f NAB sine omega t. So this is the value of phi. I have put this value into equation number 2. So the equation for induced EMF E is given there. So E is equal to E0 sine omega t. Now E is equal to E0 sine omega t. It is written like this. So if you compare this equation with the above equation, E0 will be equal to 2 pi f NAB, because already sine omega t is there. So therefore we can write here instead of this E0, 2 pi f NAB. So this is the peak value of EMF, which is denoted by E0, where E0 is nothing but this much. It is the peak value. So, and this is called as an AC generator. This peak value, this is called as AC generator. So if we plot a graph of change of this phi, so we can get here 0 pi by 2 pi, 3 pi by 2, 2 pi and 5 by 2. So how this particular thing changes? See here, if the phase difference changes like this, 0 pi by 2, 3 pi by 2, 2 pi, 5 pi by 2, 6 pi and 7 pi by 2. In this way the phase angle is changing here. Since the value of phase changes like this, then how the EMF changes? See here. The EMF changes as initially it is 0, then it is maximum, then 0, then minimum. Initially for 0 it is 0, it is plus E0, then it is minus E0, then 0 and minus E0, then 0 and plus E0. In this way the value of the graph will be there, so readings will be there. So the AC generator will be like this. If I plot the AC generator here, then the values will be, you can look like this. As this is 0, this is pi by 2, this is 2 pi, this is 3 pi by 2, and this is 3 pi, 5 pi by 2, and 6 pi, sorry 3 pi, and 4 pi, etc. 7 pi by 2 and then 4 pi, etc. In this way we can get the graph, relative graph to this AC generator. So this is about the coil rotating in a uniform magnetic field of induction. And now let us turn to the next article, that is power in SCR. Power in SCR. So what is this SCR? This is inductor, capacitor and resistor circuit. So dear students, you might be knowing how the SCR can be drawn. See here, this is inductor, then capacitor, and this is resistors. In this way, it is put across a AC generator. So we are going to find out here, or we are interested to find here, the expression for power in SCR circuit. So you might be knowing that if this source of AC is here, which is having the EMF E is equal to E0 sine omega t, the inductance or the reactance across this is called as XL, whereas reactance across this is XC, and the resistance across this resistance is called as R. So if we are interested to find a power in LCR circuit, if the current flows through this particular circuit, then the value of current is I is equal to I0 sine omega t. Right? The value of EMF is E is equal to E0 sine omega t, and the current flows through the circuit is I is equal to I0 sine omega t. Suppose equivalent EMF and current I are having the phase difference phi. What is saying that? Suppose the equivalent EMF and the current I are having the phase difference phi. So in this way, if there is a phase difference of phi between the current and the EMF, then the power in LCR is the scalar product of EMF and I. So the power in LCR, which is the scalar product of current into EMF, it is given by P is equal to, the expression for power, P is equal to EI into cos of the angle between them, that is phi. So in this way, the angle phi is used here. So sorry, the phase difference is phi. So the expression, putting the values of E0 and I0, E and I we get here, P is equal to, what is the value of E? It is E0 sine omega t. And what is the value of I? It is I0 sine omega t into cos phi. So that can be written as P is equal to E0 I0 sine square omega t into cos phi. So this is about the expression. Now let us see the E0, I0 and cos phi into, let us take the average of sine square. So that can be written as P is equal to E0, I0 into cos phi into the average of sine square omega t, average from 0 to 2 pi. So that average is E0 by root 2 into I0 by root 2. That is cos phi into 1 by 2. So that can be written as pi is equal to E0 I0 cos phi into 1 by 2. So now let us go ahead. That can be written as P is equal to E0 by root 2 into I0 by root 2 into cos phi. It is one and the same. Hence root 2 multiplied by root 2, hence root of 4 and square root if we are taking out, then it will become 2. So the same equation is written in another form there. So P is equal to ERMS into that I0 by root 2 is called as root mean square value of current. So IRMS into cos phi. So in this way, ERMS into IRMS into cos phi, the expression for power in this LCR circuit. So this power is called as P2. Whatever power we have calculated is called as P2. This power is called as P2. Whereas apparent power is also there. So P apparent is nothing but ERMS into IRMS. And P apparent is nothing but ERMS into IRMS. So the product of root mean is square value of current and root mean is square value of voltage is nothing but the apparent power. Hence, the ratio of P2 to Pm is nothing but power factor. Let us take the ratio P2 to the P apparent is called as power factor. In this way, we have reduced the expression for power factor here, which is nothing but ERMS into RMS into cos phi divided by ERMS into IRMS. After deduction, we will get power factor is equal to cos phi. Means, see here, the value of P2 is what? ERMS into IRMS into cos phi. It is true power. And what is the value of this apparent power? It is ERMS into IRMS. So this is what we are talking about, the ratio, and after deduction, the power factor is equal to cos phi. So in this way, this power factor PF is also denoted by R by Z. This is the power factor in LCR circuit. So in this way, we have reduced the expression for power in LCR circuit. So after this, let us do some practice of numerical problems based on NEET or CT examination. Okay, we shall stop here.